start the recording. And let's go ahead and start talking about capacitors and stuff. And if you guys haven't already, if you could fill out the attendance form, that'd be greatly appreciated. So the first thing we want to know is, what exactly is a capacitor? What's your guys' best understanding of what a capacitor is? And also, what is capacitance?
I think for a capacitor, I think really the simplest way to understand it would be just a form of it's just a way to the way a object holds or stores and releases energy. Right?
So you're saying that's what capacitance is?
No, that's what a capacitor does.
Okay, so yes, that's what a capacitor does. So it somehow stores and releases energy. And how does it do that?
With the battery that is attached to the circuit.
And how does it store energy? What does it actually store?
Isn't it the electric field between the two plates?
And how is that electric field generated?
Because you have a positive and a negatively charged plate.
Exactly. The answer I'm looking for here is charge. So the capacitor stores charge, and that's how it stores energy. And so capacitance is, I think, quite literally, if you Google capacitance definition, it's literally like the ability of a system or something to store electric charge. So that's what a capacitor is. It's and in this case, it's you guys are only worrying about parallel plate capacitors, where essentially you have two parallel plates, and they store charge where one side is positively charged and the other side is negatively charged. And so, how is the capacitance of a capacitor related to the charge stored, and then also the potential difference across the plates? How do we relate charge, capacitance, and voltage?
Capacitance is equal to charge over changing voltage.
Yep, exactly. And you guys have that in your formula sheet, where the capacitance is equal to the charge stored on the plates over delta V. And what exactly is this charge Q here? Is that the total charge being stored on both plates combined? Or what exactly is it?
Isn't it the charge of each plate?
So, what do you mean each plate?
The charge that's found on the positively charged plate and the negative charged plate.
So you're saying the positive plate is plus Q and the negative plate is negative Q?
Yeah.
Yep, exactly. So the charge Q is the magnitude of the charge on each plate. One's positive, one's negative. So let's go ahead and hop into some examples, because pretty much this is all you need to know for capacitors. This and understanding how capacitors work parallel to one another and in series. So we're going to go ahead and we're going to have a capacitor, C1, and we're going to go ahead and hook it up. That's a horrible battery drawing. There we go. So we're going to go ahead and have capacitor C1. It's going to be hooked up to a battery V0. So we want to know what's going to happen if we go ahead and connect a second capacitor in series with C1. So we're going to go ahead and connect a second capacitor here, C2, in series with C1. So we want to know how's the charge in C1 going to change. Let's take 3 minutes, then we'll talk about it. All right. So how is the charge on C1 going to change if we then go ahead and connect another capacitor, C2, in series with it? So first of all, we want to understand what's the total net capacitance of this new, essentially if we go ahead and combine C1 and C2 into one capacitor, what's the total net capacitance going to be? The new net capacitance.
It'd be like 1 over C1, or yeah, it'd be like 1 over C1 plus 1 over C2.
Yep. So you're saying it's the whole like adding the reciprocals, whereas 1 over C12 is equal to 1 over C1 plus 1 over C2.
Yeah.
Yeah. C1 plus 1 over C2, and then we have this to the negative 1. Or another way you can actually write it, you can say it's C1 times C2 over C1 plus C2. It mathematically the exact same thing. Okay, so does he give you that? No, he just gives you the 1 over relation. But so that's going to be our new net capacitance. And so what's going to happen to the charge on C1 if C2 is connected? Is our total charge on C1 and our total charge on C2 going to be the same? Or is it going to be split as a fraction of the capacitances?
It's going to be the same.
It's going to be the same, right? And how do we find that new charge?
The capacitance times the voltage.
You're saying the capacitance for the total capacitance or just for C1?
Just for C1.
Just for C1? I thought you just said that the charges are going to be the same.
Oh, right, yeah. Then we can just find it for the whole thing.
Yep, exactly. So we know for a single capacitor, the charge is equal to the capacitance times the voltage. And in this case, we know that the charge is going to be the same for our two capacitors. And so to get the charge on each of them, we want to go ahead and find the total net capacitance of the entire series and multiply it by our voltage here, which in this case is just V naught. Does that make sense? Essentially, we go ahead and imagine this where we have this single C12, and we know the total voltage drop, which is going to be V naught. Why is the voltage drop across C12 V naught? Have you guys talked about the loop law for voltages yet?
Is that where, like, if it's like on a continuous loop, it's for... Yeah, if it's a continuous loop, then it's parallel, but if it's like connected by a wire and there's no node in between the series?
Not quite what I was asking. I'm talking, have you guys talked about the voltage around any loop in a circuit?
Don't think so.
Okay. It's sort of weird where it's like, because I think you guys don't mention it until next week. So unit 13, when you start talking about resistors and circuits with resistors, but it's really helpful to know for understanding capacitors. Essentially, any loop in any circuit, so like around this loop here, the total voltage is going to be 0. So we gain 12 volts through the battery, or we gain V naught through the battery, so plus V naught, and then we lose V naught going across the capacitor, minus V naught. And so that's how we know what the voltage drop across C12 is. Just, I don't know why he tries to have you guys understand capacitors without mentioning that, but I personally think it helps. But so, as you mentioned, the charge is the same for both capacitors. And we know that it's going to be the total net capacitance times our total net voltage drop. Is there any questions about that?
Yeah. So the charge state is like it's gonna be the same as like the total charge between the two capacitors, but like does the actual like charge go down?
So that would depend on whether C12 is greater or less than C1. And that would have to deal with whether C2, like essentially how you add them together. If we want to actually use numbers, let's say C1 is 5 farads and C2 is 3 farads. The total new net capacitance, 1 over 5 plus 1 over 3 ends up being, and then 1 over that ends up being about 2 point something, or a little less than 2, a little less than 2. So the C12 is less than C1. So yes, because the capacitance goes down, the charge would have to go down.
Okay. That makes sense.
I just have to think about that in my head. Because, yeah, if you connect two capacitors in series, the total net capacitance is going to be lower than both individually.
Mm-hmm. Yeah.
Okay. So, Kevin, did you have any questions? I saw you were typing something in the chat for a second. You don't have any questions? All right. So let's go ahead and hop to the next one. So what's going to happen to the charge on C1 if C2 is instead of being placed in series, if it's instead placed parallel? So we're going to have our two capacitors parallel with one another. Let's take 3 minutes, then we'll talk about it. All right, so now we have our two capacitors being placed in parallel, and we want to try to understand how the charge on C1 is going to change if it's placed in parallel. So, first of all, is the charge going to change at all?
No, the charge wouldn't change, right?
So we have two conflicting answers here. Who's correct? Well, first of all, let's try to think about it where is the voltage drop across C1 going to change? Remember the loop law we just mentioned a few minutes ago? The voltage around any loop in a circuit is 0, right? So for this loop around here, we start at the battery and we only go through C1. We're not going to go through C2. We gain plus V naught across the battery and we lose V naught across C1. Same thing for if we go through the battery, up through C2, and back down to the battery without going through C1. So essentially, our voltage drop across C1 and across C2 are both the exact same, and it's the original voltage drop, which is just V naught. So how do we get the charge on C1 from the voltage drop? If we know the voltage drop across each, how do we get the charge?
We can do charge equals capacitance times, or C12 times the voltage.
Do we have to take into account the total net capacitance here?
No.
Exactly. Remember, we only care about the charge on C1, right?
Yeah.
And we know the voltage drop across C1, which is V naught, and we just multiply by the capacitance of C1. So the charge is just the capacitance of C1 times V naught. Isn't that just the original problem here if we ignore C2?
Mm-hmm.
Yeah, there's no change in the charge. Yep. I mean, if we connect a capacitor in parallel, there's going to be no change in the voltage drop and no change in charge. Pretty much nothing is changed here. And you guys will actually see there's some things that are changed once you get into more circuit stuff next week. But regarding the charge and the voltage drop, there is no change if you connect capacitors in parallel. And Harsha, you just mentioned C12 if we had the total net capacitance. How does the total net capacitance here change? For two...
It increases, right? Because you're adding the two capacitors together to find the net capacitance.
Yep, exactly. So we have no change. And just for fun, even though we didn't need it for this problem, C12 is equal to C1 plus C2 for parallel. Having X capacitors in parallel is the same as having just the one capacitor. Pretty much. I mean, at least in terms of the charge and the voltage drop across each capacitor, it would be the exact same as if it was just that one capacitor alone. Does that make sense? And then the total net charge, obviously the total net charge being stored in the entire circuit increases because we connect the second capacitor and now that's storing charge as well. But the charge on each individual one is unchanged. Anyone have any questions about that? All right. And by the way, welcome, Sarah. Let's go ahead and hop into part C here. So we want to know, how does the charge on C1 change if C2 is going to be placed in series and a dielectric with constant kappa is placed in between C1's plates? So essentially, we have our battery. We're going to have C1, C2, and we're going to go ahead and place a little dielectric in there. We'll color it like orange. With constant kappa. how is the charge on C1 going to... I mean, what's going to be the new charge on C1 in this scenario? Let's take like 5 minutes, then we'll go over it. And welcome, Jonathan. Working on part C right now. Dielectric is supposed to be placed in between C2's plates. For this problem, we're placing the dielectric in between C1's plates. So we're placing them in series, and the dielectric is placed between C1's plates. All right. So we're taking our second capacitor C2, we're placing it in series with C1, and we're placing a dielectric with constant kappa in between C1's plates. So how do we get the new charge on C1 here? First of all, how would this be similar to the first problem where we have C1 and C2 in series without the dielectric? What's the main thing we remember from this one?
Adding up the capacitances with the reciprocal.
Mm-hmm. So, I mean, first of all, we want to be able to find the total net capacitance. And how can that get us the charge?
Because Q equals BC or CV.
Yep. So the charge on capacitors in series with one another is going to be the same. So we know the charge on C1 now is going to be the same as C2, which is going to be the exact same as if we have one total net capacitor, C12. So how do we get the total net capacitance? Well, Harsha said something about C12 is going to be, we add them to add the reciprocals. This whole 1 over C1 plus 1 over C2 to the negative 1. It's mathematically equivalent to multiplying them all together and adding them. So is that all we need to do here? Or do we also need to take into account anything else?
You have to account for the dielectric now.
Mm-hmm. What does the dielectric do?
I think the equation is just kind of scales the capacitor to the capacitance. The new capacitance will just be kappa times the old capacitance.
For just C1?
Well, I guess since they're in series and they're multiplying together, it'll be kappa times C1 times C2.
Mm-hmm. So does that mean we're going to have a kappa up here? Does that mean we also have to multiply an entire kappa down through here, and so they cancel out? Or what happens? Well, the dielectric is just in C1, right?
Yeah.
Yep, exactly. So we only have to take into account the kappa for just C1. So you go ahead and write this with a bit more room. So we have C1 times C2, and we also have to take into account the kappa because the new capacitance for C1 is kappa times C1 over kappa C1 plus C2, which once again, the multiplying divided by the addition is the exact same thing as the 1 over plus 1 over plus 1 over. And so that's how we get our total, a new net capacitance. And then same thing for problem A. The charge on C1 is just going to be that total net capacitance times the voltage drop, which is just V naught. Anyone have any questions about this? All right. So let's go hop into the next one. So how is the charge in C1 going to change if a slab of conducting metal is placed between C1's plates so it covers half the distance between them? So essentially we have our battery, we have our capacitor, and then we have a conducting slab that covers the distance about halfway between them. Let's make it gray. Why not? So how is this going to affect our charge? And what's the new charge going to be? Let's take 3 minutes and we'll go over it. All right, so we have our conducting slab and we're placing it halfway between our two sides of our capacitor. So it essentially actually doesn't matter where we place the conducting slab, but it takes up about half the distance between our capacitor plates. So how is this going to change the charge on C1? Well, first of all, how is this going to change the capacitance of C1? What does placing this conductor here effectively do to the capacitor? Yep, exactly, Kevin. It effectively halves the distance between the plates. So how does that affect the capacitance? What does halving the distance do?
If you half the distance, then that would increase the capacitance.
By how much?
Twice, 2 times effect.
Yep, exactly. So we know the capacitance from our equation sheet. One way we can relate capacitance is going to be epsilon naught times the area of the plates divided by the distance between them. If the distance decreases by 1/2, then the capacitance would have to double. So the capacitance is equal to 2C1, and then we know the charge is just C times V naught, which is equal to 2C1 V naught. So essentially, our charge ends up doubling. Does that make sense? Anyone have any questions about this? All right. So let's hop into the next one. So we're going to have our charge on C1, and we're going to go ahead and disconnect the battery. And then after the battery is disconnected, we're going to move the plates closer together. So we're going to halve the distance between them. How is the charge on C1 going to be affected? Let's take 2 minutes and we'll talk about it. All right, so we're disconnecting our capacitor and then moving the plates closer together. First of all, is the charge going to change at all?
No, the charge stays constant since the battery's disconnected.
Exactly. Battery's disconnected, so the charge has nowhere to go, and so it can't change. So what does change in this case? The charge stays constant.
Voltage,
The voltage changes how?
it would decrease.
It would decrease. And what else happens to increase? What increases to keep the charge constant?
Capacitance.
Yep, exactly. The capacitance. So we move the plates closer together. That increases the capacitance. It doubles it, actually. And then we know that because the charge stays constant, because it has nowhere to go, the voltage has to drop by half. So Q, no change. So now, part F, how does the charge on C1 change if C2 is placed in series and then the battery is disconnected and then the distance between the plates on C2 is doubled? So we're going to have C1 here. We have our battery. Then we're going to go ahead and disconnect the battery and then increase the distance between C2's plates. Let's take 5 minutes and we'll talk about it. All right, so how do we, first of all, approach this problem? So we're going to connect C2 in series, and then the battery is going to be disconnected, and the distance between the plates on C2 is doubled. So, first of all, what's the first step? First, we connect C2. How is the situation going to change here if we connect C2 in series?
I think we'll have to first find the equivalent capacitance when you connect the second capacitor.
Mm-hmm. Right, it's the same thing as the first problem. First, we find our new equivalent capacitance. So we have C12 is equal to C1 C2 over C1 plus C2. And then we know the charge is then C12 times V naught. Boom. We already did that for part A. So then the second part, we're going to disconnect the battery. And we know disconnecting the battery initially isn't going to change anything. And then we increase the distance between the plates on C2. How is that going to change the charge on C1 if the battery is disconnected?
Well, we know that the charge wouldn't change if we disconnected the battery.
Yep, exactly. Straight up, boom. There's our answer. We know the charge isn't going to change after the battery is disconnected. So, boom, this is just, our final charge is just C12 V naught. We know that after the battery is disconnected, nothing's going to change in terms of the charge on our capacitors. Straight up. So it doesn't matter what we do with C2, the charge is still going to be the exact same. At least on C1. And then also on C2. Does that make sense? Anyone have any questions? All right. Let's hop into part G here. So how is the charge on C1 going to change if we place C2 is parallel and then the battery is disconnected and then a constant kappa, a dielectric with constant kappa is placed between C2's plates. So essentially we have our battery down here. We have C1, then we have C2 up here with our dielectric in between C2's plates. And then we know that we've gone ahead and disconnected the battery after connecting C2 before we put the dielectric. Let's take 5 minutes, then we'll talk about it. And if my wording there was not clear, because I'm pretty sure it wasn't, feel free to ask a question. All right. So we're first connecting C2 in parallel, then we're disconnecting the battery, and then we're placing our dielectric in between C2's plates. So let's break this down step by step. How is the charge going to change for the first step when we connect C2 in parallel? Does anyone remember how it works? It won't change, exactly. For the first step, when we connect C2 in parallel, we know that our total voltage drop across C1 doesn't change because for each loop, our voltage drop is the same. And then we know our voltage drop, and then we know our charge is just our capacitance times the voltage drop. Because the voltage drop doesn't change, there is no change in charge. And now the second step, we disconnect our battery. So then we just have our two capacitors parallel to one another, and that's the entire circuit. And then we place dielectric with constant kappa between C2's plates. So is our charge on C1 going to change at all? How does the dielectric affect the capacitance of C2 and the voltage drop across C2? Give you a hint. Is there any battery here? Our battery's been disconnected, right? So does that mean our charge is going to change at all?
No,
no,
the
it
charge
can't.
won't.
I've tricked y'all. The charge will change. But how do we actually quantify how it's going to change? See, Kevin's typing for a second. I want to see what he says. We have to calculate the equivalent voltage. It's a good start. You're not sure? Okay. So, do we remember our loop law where the total voltage drop around any loop is going to be constant, right? So we know that the total voltage drop around any loop is going to be 0. So we know that the voltage drop across C1 is going to be the exact same as the voltage drop across C2, right? That's when the battery is connected. When we disconnect the battery, we still have this loop here where before, if we draw our loops in this direction where we're going from left to right across the capacitors, the voltage drops are both the same. In this case now, if we draw a loop, we go left to right across C1, so we lose V0. We go the opposite way across C2, so we gain V0, and it's still a net 0 voltage. Right? And we know the voltage is related to the charge and the capacitance. And we know the voltage isn't going to change. The voltage is going to stay the same for our two capacitors, right? Our total charge is going to stay the same. Sorry, that's what I meant. So we know that our charge on Q1 plus our charge on Q2 initially is going to be the same as the total final charge. Q1 plus Q2 for final. Initial, final. And because we place the dielectric in C2, the capacitance of C2 increases, right? So the capacitance increases, and because the voltage is going to stay constant, we know the charge on C2, right? Remember how capacitance is equal to charge over delta V? We know that because our capacitance increases and our voltage has to stay the same, our charge on C2 has to increase. That means the charge on C1 has to decrease. Does that make sense? I'm actually now realizing, if I think about what I just said, it didn't make any sense at all. At least I'm self-aware about it. Now, real talk, this problem's really annoying and you won't see anything like this. But I wouldn't worry about it too much because most of what you'll be seeing is just basic capacitors in series or in parallel. And if you have a dielectric, you won't have anything in series or parallel. So let's go ahead and ignore this problem because it's annoying. And let's go ahead and do the last one real quick. So we have our capacitor C1, and we have two more capacitors, C2 and C3. One's going to be placed parallel, and one's going to be placed in series with C1. So essentially going to be like this. This is C1, then we're going to have C2 here, then we'll have C3 up here. And we're going to go ahead and place our dielectric in between C1's plates. And we're not going to disconnect the battery, because the reason this problem up here was so annoying is because we disconnected the battery. So, does anyone know how our... Let me just finish this visual. No! There we go. So we want to go ahead and find how the charge on C1 changes, or find our new charge on C1. Does anyone know how we would start with this? We don't quite have enough time to give you guys 5 minutes to work on it. What's the first thing we would want to do to find the charge on C1? First of all, what would be the total new net capacitance for the entire thing? C123. How do we find our total new net capacitance? Yep, exactly. C123 is going to be C12 plus C3. So I'll have the C3 here. And how do we get C12? C12 is equal to C1 plus C2. Is it C1 plus C2 to the negative 1? Or reciprocals, exactly. 1 over C1 plus 1 over C2 to the negative 1. And I'm going to go ahead and write that as C1 times C2 over C1 plus C2. And then we also, last thing, have to take into account our dielectric, right? Where we have kappa in front of both of our C1s. So that's how we get our total net capacitance. And we know that our total charge, right? Our total net charge is going to be Q12, where it's the same charge in Q1 and Q2, plus our charge on Q3. And we know our charge is going to be C123 times V naught. And now we just want to solve for Q12, right? Because that's our charge on C1, which also happens to be our charge on C2. So Q12 is equal to C123 times V naught minus Q3, which, does anyone know, how do we get Q3 here? Remember, how do we get the charge on capacitors parallel to one another? it's going to be the exact same as if the capacitor was alone in the circuit, right? If we just completely ignored C1 and C2 and we just had battery and C3, right? Which, and that charge would just be C3 times V naught. So basically our total charge Q12 is just going to be C12 times V naught, right? Our total capacitance of 1 and 2 together times our voltage drop across 1 and 2 together. Right? We're taking our ideas that we had before, where we know that capacitors in parallel, the charge across them is the same as if each of them were just alone, ignoring the other. And then because of that, and then we know the charge on two capacitors in series is going to be the same, we just go ahead and solve for Q12. Does anyone have any questions? Wouldn't have thought that would be kept in mind. Trust me, you probably don't have to worry about problems like this at all, because the stuff you'll see on your quiz tomorrow is going to be a lot simpler. And the stuff you're seeing on your homeworks is generally not as annoying as this, where you have things in series and in parallel and dielectrics and all this other crap going on. It's generally a lot simpler. And if you can at least somewhat understand these problems, you're going to be completely set for your quiz tomorrow, where you're going to see stuff that's much simpler. All right. Well, that's it for today's session. Thanks, guys, for coming. Hope this helped out more than it hurt. Because I know capacitors were the one thing I freaking hated from this class when I took it. And I still quite dislike capacitors. And honestly, I disliked capacitors up until I learned how to do complex notation for them in electronics lab. But that's a whole nother monster that is not too fun to get into if you aren't comfortable with complex numbers. Thanks and yes, sir. Yeah, capacitors suck. Boo. But you guys still have them for another few weeks. All right. Thanks, guys, for coming. Good luck on your quiz tomorrow.